Good morning or good afternoon, depending on where you are at, and very warm welcome to more than 650 sites that they have registered to listen to our May 2024 monthly webinar. We are delighted to have with us Dr. Khaled Mahmoud, Chief Bridge Engineer with BTC in New York City. The title of the webinar is Condition Assessment of In-Service Bridge Cables using an Innovative BTC Methods. During the registration process, we did receive a number of the questions, and time permitted, we're going to try to answer them. Paul Lyles and Jamal from the Federal Highway Administration will be moderating the question and answer period. But if you have some additional questions, please, by all means, just post it on the dashboard. We'll try to get to them as time permitted. A couple of important news about the conference that will be held, our next conference in December 11, 12, 13 in Miami, Florida. And the deadline is May 30. So you've got a couple of weeks. If you have some abstract that you would like to submit, it's online that you can apply and send your one-page abstract. The conference is co-sponsored by Federal Highway Administration and 33 State Department of Transportation. We appreciate their sponsorship. We have 6 keynote talks that is scheduled. Michael Knott on what bridge designers should know about the ship colliding bridge. We have speakers from South Korea and Switzerland to give you an international perspective. We also have keynote talks on the artificial intelligence, 3D printing, and some of the new innovations at the Federal Highway Administration. We also have on Thursday night, we have a workshop that is free on utilizing the ultra-performance concrete. The instructor is going to be Eugene Gruweiler. That workshop is going to be 2 hours, discussing the optimal use of UHPC, design a step for using a UHPC for strengthening and durability, detailing, and cost. So it's a very interesting workshop that will be during the conference, and it's free in the evening. Registration is open. Please go to our site, take advantage of the early bird rate. There will be a reception on Wednesday night. There are travel scholarship that is available, and all you have to do is go to our website, and there is just a very simple application that you can fill out. And these travel scholarships are only for the U.S. state and the county bridge engineers, basically the bridge owners in the U.S. There are some limited opportunities for exhibit. Again, all the information is on our website. And also, if you plan to come, December is a very busy time in the Miami, Florida. So please reserve your rooms. There is a link on our website that you can reserve your hotel room and the special conference rates. There will be a award program that we are going to be sharing more information. So at this point, I'm going to turn it to Kathy, who is going to share with you some additional news related to the bridge engineering region. Kathy?
Thank you, Torad. I'm really looking forward to the conference. Now I'll share with you some upcoming events from our industry. First is the Engineers Society of Western Pennsylvania is presenting the International Bridge Conference, the IBC, from June 3rd to the 5th in San Antonio, Texas. See the link on the screen for more information. Next is our partners at the American Composites Manufacturing Association are presenting the Composites Sustainability Today conference in Denver, Colorado from June 4th to the 6th. Again, more information can be found at the link on the screen. An additional upcoming event is the 4th International Bridge Seismic Workshop, which is presented by the Canadian Association for Earthquake Engineering and Seismology and Carleton University, which will be from August 11th through the 14th in Ottawa, Ontario. Again, more information can be found at the link on the screen. Next, while this is not an event, our partners at the NSBA have asked that we announce the release of a new version of their bolted splice spreadsheet. They're now at version 3.15. The link on the screen will take you to the revised spreadsheet. If you have questions, please contact Vin Bartuka at the email shown below. Now for our IBT, ABC, UTC upcoming events. Our next monthly webinar is Thursday, June 13th from 1 to 2:15. The featured presentation is the Dogwood Bridge replacement utilizing press brake tub girders. We'll be joined by officials from Imperial County Public Works, as well as their design partners from NV5 and Belmont. This is a local government-led project, and it has received, it's received national award recognition. So please mark your calendars and join us for next month's webinar. Our next quarterly research seminar is July 26th from 1 to 2:15. We'll be talking about the project for comprehensive decision support tools for ADC considering social equity. This project will be presented by the research team from Florida International University. Please mark your calendars for that event. Our final announcement for today is the in-depth web training, which is scheduled for Tuesday, September 10th from 11 to 3:15 Eastern. So the format of the in-depth web training is similar to our webinars, but it gives us some extra time to delve into the details of the topic at hand. And this year's topic is innovations in ultra-high performance concrete. We're being joined by our presenters, Atorad Azizanamini, Benjamin Graybiel, Eugene Breweiler, Sam Falaha, and another presenter yet to be determined. On the next slide, we have our modules for this innovative ultra-high performance concrete training. We'll be talking about UHPC shotcrete, 3D printing utilizing UHPC, UHPC overlays for bridge deck rehabilitation, a UHPC design example, and we'll also get updates on the structural design and specification guidance that is in process. That brings us back to today's webinar. Today's featured presentation is on condition assessment of in-service bridge cables utilizing the innovative BTC method. We are joined today by Khaled Mahmood, who is the Chief Bridge Engineer for BTC in New York City. I'd like to remind everyone that there is a question and answer session following the presentation. And please post your questions in the question and answer box. Now we'll turn the presentation over to Khaled.
Thank you, Kathy. Good afternoon, everyone. It's a pleasure to be here. We're going to talk about condition assessment of in-service bridge cables using the innovative BTC method. The BTC method is a patented methodology for the evaluation of strength and forecast of cable life of suspension cables, cable stay bridge stay cables, and strands of pre-stressing in segmental and pre-stressed girders. Here's an outline of the presentation. We're going to talk about why we inspect bridge cables and the methods that are used currently for the evaluation of bridge cable strength, the BTC methods, and the visual-based corrosion methodology in NCHRP 534 that was published in 2004. This has been updated with a document by NCHRP 12-115, which is also having a web-only document named or dubbed NCHRP 353, published in October of 2022. Not to be confused with the synthesis, NCHRP synthesis that was published back in the day, carrying the same number, 353. We will look into the risk matrix that we consider in the BTC methods and the process that we follow in the BTC method in terms of inspection, sampling, wire tests, and the strength evaluation. The inputs for the cable strength evaluation per the BTC method as to the broken wires, cracked wires, and the mechanical properties of the entire stress strength curve, including both the ultimate strength, ultimate elongation, as we work with an energy principle, where the area under the stress strength curve is a measure of the energy that it takes to break a wire. And we will finish with the forecast of cable life, a very important feature of the BTC method. The method has been published in 2 reports of the FHWA. The first is the primer for the inspection and strength evaluation of suspension bridge cables, was published in 2012, and a New York State DOT report C0711 that was published in 2011, and it's co-sponsored by New York State DOT, New York State Bridge Authority, and FHWA. The method, the BTC method, has been applied on the Williamsburg Bridge cables in New York City, the Pierre Laporte Bridge in Quebec City, Canada, where we applied the method to evaluate the strength and the forecast of life of the main suspension cable, as well as the condition assessment of the suspender ropes, the helical ropes, where we forecasted the life of the ropes and actually worked on the prioritization program for replacement of the entire set of suspender ropes. That's currently ongoing. The BTC method has been applied on the Fourth Road Bridge in Edinburgh, Scotland, and on the Bronx Whitestone Bridge in New York City over the East River, and on the Mid-Hudson Bridge over the Hudson River in Poughkeepsie, about 90 miles north of New York City. Beautiful scenery up there. We have been on the design review and fabrication construction support team for the Yavuz Sultan Selim Bridge, which is basically the 3rd Bosphorus crossing in Istanbul. It's a suspension cable stay bridge hybrid style of structure. It reminds you of anything of the Brooklyn Bridge, and it is the longest suspension bridge that carries both railway and roadway traffic. The BTC method has contributed to the fabrication specifications, which has a lot to do with the longevity of the design and the life of the cable. We had very much the same role on the 1915 Çanakkale Bridge in Turkey that connects also Europe and Asia over the Dardanelles Strait. This is now the longest suspension bridge in the world. Why we inspect bridge cables? I have a very good question. You look over here, it's an actual replica of a long span cable, and what you have here is upward of 27,000 wires in the cable cross section. Over time, these wires would degrade to different degrees of deterioration in terms of embrittlement. We'll see what that means. Plainly put, that is the loss of ductility. They will have cracks. Some of the wires will break. So a proportion of the cable cross section you see, in general, not this particular one, they will have proportion that's broken, proportion that's cracked, and proportion that is degraded with embrittlement and loss of ductility. That means loss of ductility and loss of strength. By the way, right off the bat, when we mention the word risk, this is just a term we use in reliability analysis and probabilistic analysis, the risk basically of missing deterioration. So on all the bridges I presented earlier, the existing bridges, aside from the 2 new suspension bridges I mentioned, they are ranging in age between 53 and 120 years old. And they are in good shape. They are running traffic. The bridges in New York City, I drive on them quite frequently, and the bridges overseas, I drive on them every chance I get, because it's just fun to drive over these bridges. And the risk that we are trying to quantify here is the risk of degradation, and going forwards, what to do about that form of degradation, although these forms of degradation, with the main purpose of prolonging the service life of the cables. It's very good news that the Williamsburg Bridge is past 120 years old, and a week from tomorrow, in fact, speaking of anniversaries, we're going to celebrate the 145th anniversary of the iconic Brooklyn Bridge on May 24th. So there is a lot of good news about that. So our main goal is to develop a strategy to help the bridge owners and to help our industry in prolonging the life of these strategic transportation assets. So what are the risks of degradation that we try to capture and prevent or circumvent, that they evade us to stay ahead of that, these forms of degradation? Fatigue damage that's coupled with environmental degradation, what we dub in scientific terms as stress corrosion cracking and corrosion fatigue, which is a process, has nothing to do with the visual corrosion that you see on a surface of wire. The embrittlement of the wire, which is a reduction in the ultimate elongation or reduction in ductility and the growth of cracks, and finally the breakage of wires, which is the worst thing that can happen to a wire. All these factors of risk are at play under the combined effect of the load and the environment. So the BTC method process starts with cable wedging and inspection, wire sampling afterwards from each cable opening. By the way, when we say cable opening, that basically defines the length of cable between two successive suspender ropes. So we call it cable opening, panel, cable length, and inspected. All this boils down to the distance between two successive suspender ropes. So we take the wire samples that we're going to take a look at into now, and take it to the lab, chop it into pieces, have the wire test as we're going to see later on, and then take the test results, the findings of all the inspections, and do the analysis, get the strength of the cable, and then identify the cable strength today, and then do further analysis based on the data to forecast the cable life. Here's an image of a suspension cable being inspected back in the day. The red color you see here is the lead paste. That was an excellent material used in the old days. We can't use it nowadays for obvious reasons. The lead component in it, it was used to cover the exterior surface of the cable, and it was sort of a barrier from the moisture, but it's not used anymore. I must add here that this cable is been cleaned after we removed the wrapping wire, which is a grease that is wound around the cable with tight laps. So that basically is applied with a pre-stressing force. And after cleaning all that, we wedge the cable, and we see the wires along the two sides of the wedge. Of course, evidently you can see all the wires in the exterior ring of the cable, if you will. But let's take a look here at the wedge pattern. This wedge pattern has been used since ever, before anybody start having that documented in NCHRP or BTC method and all. This has been an industry practice. By the way, this wedge pattern from 1 to 8 every 45 degrees going clockwise is basically an industry practice that's been used, and it's not cast in stone. In fact, we have seen, we've been on cable openings where this wedge pattern has been a bit more, 9 or even 10 to oil the cables. Please don't oil the cables anymore. It's messy, it's costly, and it didn't do what it was intended to, but that's another story for another day. What you see here is what you get. What I mean is You look at wedge 1, you see the wires only along the 2 sides of the wedge. That's it. So if you go to wedge 2, which is right there, or up until wedge 8, you don't see any wire in between the 2 wedges. You see wires only along wedge 1, along wedge 2, and so on. So speaking of that, you can see here actually that here is wedge 1. You see the wires along this way, along this particular wedge. When you go to wedge 2, you see the wires along that particular wedge, but anything in between you don't see. So this is the number of wires we see sums up to about 10%. So about 90% of the cable cross-section is not inspected, is not looked at a particular investigation. That renders the whole process to a probabilistic, reliability-based analysis, thus the BTC method, as we speak here today. When we wedge the interior of the cable, to see the interior wire of the cables, we see broken wires present themselves in this particular manner, which has a good reason because of the bend that these wires came originally on from the manufacturer, and was that left a permanent bend in the wires. And you see here the interior broken wires. One thing that to say from the get-go, that all these broken wires are embrittled. If we zoom in on the end of the broken wire here, you see that the wire is full cross-section. This wire is about 80 years old when this picture was taken. It has the full cross-section, full diameter, no necking, but embrittlement is vivid and clear. We do the wire samples. What you see, this yellow donut is basically defining what we consider the pool of wire samples. What we say is we do not sample a wire from here. Why not? You told us that some cables that have more than 27,000 wires, on average, you find the cables with 10, 12,000 wires. So how does it hurt to take a sample here and just leave it alone without splicing? Well, the problem with that is you leave a void. It's not a 1 wire or 20 or 2 or 20 out of 27,000 or 15, 16, 18, 20 out of 12,000. It is the matter of leaving a void that hoists moisture and debris and whatnot, and that's not a good thing. So we define a pool of wire samples that we take the samples from, and that depends on the diameter of the cable and how deep we can take a wire out and splice it back in, and you'll see what I mean in a couple of slides. So what we define here is random sampling from each wedge, or whatever the random sampling we provided with the BTC method, random sampling process to basically avoid the visual bias or avoid the subjectivity of the inspectors. And the news is, when you look at these wires, good, bad, or ugly, they all, for the most part, they don't look that happy with the stew of acid rain, de-icing salt and de-icing materials and debris and you name it. There is a stew of many, and you add to that the lead-based paste on the surface of the wire that, of course, sips inside the cable cross-section. In other words, we try to eliminate all that, weed out this kind of bias, and do the random sampling. And that's what you see here identified in this picture. These are the tags that identify the particular sample in that wedge within that pool of wire samples. So after we take the sample out, we are able to get in these great guys from the contractor. They are using a come-along chain that you see here, and with jacks, And what you see here with the under the plier is a turnbuckle that is used to splice the wire. You'll see a better picture of it. I actually have a sample here on my desk somewhere. I can show it later on. And with a couple of pliers, a pair of pliers here on opposite side, because the turnbuckle is designed that way. You tighten the wire and you bring it back to service load, or with a load cell to measure the load in the wire. So it is surgical with very rudimentary appliances. And here is the turnbuckle sitting comfortably, and the new wire is back where we took the samples. So we don't do destructive anything. In fact, we are very careful when we do that. We do it with surgical precision. If we cannot reach a wire, then we don't sample it, period. So now to the wire test per the BTC method. And by the way, all these processes, I mean, the BTC method sampling plan has been applied on all almost all the, with the exception of one bridge that we had the test results already. But we done the two methods are done in parallel, so there is no duplication of the sampling. There is no duplication of the inspection efforts. It is done once and for all, and then the tension test is done. And there where we start diverging. The BTC method, because of we are very keen and very watchful of the cracking conditions or the cracked wires in the cable. We like to know where they are, to what extent of cracking the wires are going through, and all this. It's very important for the accurate assessment of the strength with measurable metrics, as we're going to see later on. So we do fatigue test, and we do fractographic examination of the fracture surfaces to identify pre-existing cracks. Remember I mentioned that the wire is 5 millimeter in diameter, so it's a very small component, and we do the fractographic examination via scanning electron microscope. Thus, it's dubbed as SEM images, as I'm gonna see show it to you later on. And we do hydrogen content test. We can speak later on if there is time why we do it. But in a nutshell, we do the hydrogen content test using a fusion method in which the wire sample is basically heated to a very high temperature, so it melts and it gets into fused into a molten state, and then the concentration of the evolved hydrogen gas is detected by thermal conductivity techniques and expressed in part per million, thus the ppm. All right, so now the tensile test. Here is an image of the brand new wire. That's brand new, and it has only 6% elongation. Wow. Remember the A36 steel, how much elongation we have there? The ductility on that was like 20 to 22%, or even a bit more. So the brand new wire is 6% only. And for the ultimate strength, it is typically under 250 KSI. In fact, if you look at the project specifications for all these older bridges that I spoke of, up until maybe around mid-70s, you find that the typical minimum accepted ultimate strength was about 220 to 225 KSI, and the strain is accepted even if it's as low as 4%. Well, up until today, with the wires that we are pushing with the 1960 megapascal wire, which is basically over 280 KSI, we still accept the 4% ultimate elongation. But that's a whole discussion on its own. But moving forward here, with the wire degradation, you start seeing reduction in ductility, and you start seeing ductility. Over here, for instance, it becomes less than 1%. Oh, wow. This is like about a little below 0.8%. And over here, how about this? About 0.3% or a little over 0.3%. So these wires were taken out of the bridge cable. They were alive and well and carrying load. Case in point, or the evidence of that is they survived the stress strain, the tensile test up until a certain point, and then they snapped and broke. That is vivid demonstration of the embrittlement. And if you start looking at these three graphs, you find reduction in ductility. That's an order of magnitude between this value and this value, for instance, or even lower for some sampled wires. And the reduction in strength and the coefficient of variation and the ultimate elongation is multiples of that equivalent coefficient of variation of the ultimate strength. Moving along, we do in the BTC method fractographic examination, and it is inarguable that these are clear cracks and measured and provides wealth of data in terms of the fatigue, in terms of the strength evaluation, and in terms of the very important task of evaluating or forecasting the cable strength. So you see here the thumbnail crack. Here is actually this picture is no mystery. It is the cross section, the circular cross section of the wire that we see here. And of course, this is the cracked part. And here is the crescent shape or the thumbnail crack, where you see the wire is maintaining its full cross section, embrittled, no necking, no sectional loss. The crack goes into mode 1, which is perpendicular to the stress field, which is along the longitudinal axis of the wire. And then when it reaches a critical crack depth, it splits along the grain boundaries, and then the fracture happens on that upper surface. So here is another demonstration of these wires. These kind of wealth of information is invaluable in the analysis of the cable strength, in the forecast of life, and in the assessment of degradation. Over here, we see fatigue damage in this cross section. Again, this is a circular shape. I'm coming here to the surface and just the crescent part or the thumbnail. And if we zoom in on the area where it shows vivid fatigue beach marks that could be quantified, and we quantify that to determine the life of that bridge wire when it was taken out of the bridge cable with very high level of precision and accuracy. So now I kept saying embrittlement. So what is the difference between when we say corrosion fatigue, stress corrosion cracking, and corrosion, visual corrosion? Well, stress corrosion cracking, corrosion fatigue, those are fracture mechanics terminology. They have scientific meaning. They have the crack growth, the fatigue that happens to the wire under the effect of environmental degradation that releases the degradation process that releases the atomic hydrogen that comes into the crack tip and the crack mouth and keeps furthering breaking the interatomic bond and furthering the crack growth and results in that embrittlement. You can see a big difference between this embrittled wire and the picture on the left where the laser point is hovering here, where you see heavy corrosion and rusted through holes in the web of these sleeper beams supporting a grating on the top. And this is inarguable. There's a big difference between this mild low carbon steel and the very high carbon steel that exists in the bridge wire. It's a different phenomenon. In fact, case in point, when was the last time we had to replace cable bands on a suspension cable because the cable lost mass or lost weight, for that matter, because of the loss of material The answer is never. So you see here the impactful effect of cracking and embrittlement that go hand in hand from that brand new wire over time that would decrease in ultimate elongation up until it reaches this very low level or even lower. Had we left this particular wire in the bridge cable, it will be getting broken very soon because it has very low ultimate elongation, and with further crack growth, this ultimate elongation will be further lower and lower and lower up until the wire breaks. And actually, I mentioned the energy under the stress strain curve. You can imagine the level of energy that is included here under this wire. That's very healthy, and this is much lower, of course, level of energy, but over here is a sliver of the energy on that previous one. And you can now appreciate the impactful effect of cracking and embrittlement. This picture shows, or what I've talked about so far, is the wedging and suspension cables. If we have time, I'm happy to talk further about our work, and not in the much details that I would love to, because confidentiality and confidentiality agreement we had with some bridge owners not to reveal the work there. So, but I will leave that at this point in time. Fracture-based analysis of cracked wires that is used in the BTC method. Of course, when we have a cracked component, any structural steel component that has a crack, all the elastic analysis that we so carefully do with finite element and this and that is invalid, is insufficient. What takes over is the fracture parameters, and in terms of that, the K sub C, which is the fracture toughness of the bridge wire, that was an unknown quantity before our work. We introduced that in our patent and quantified the K sub C, which is basically equivalent to the Charby V notch of the wire material. That's correlated to the sigma cracked, which is the ultimate strength of the cracked wire, and the A sub C here is the critical crack depth measured in the specimen at rupture, and Y is a crack geometry factor. The steps involved in the BTC method, in a nutshell, we use the inputs of the entire stress strain curve given that energy principle I alluded to earlier. We describe every component of the stress strain curve, ultimate strength, like you see here, with a proper probability distribution, the ultimate strain, Young's modulus, and yield strength. We provide as an input probability of broken wires. If you see 5 or 6 wires during inspection, it doesn't mean that you have 5 or 6 wires in the entire cross section. Of course, remember, we see only about 10% of wires in the bridge cable when we do the inspection, and we do the probability of cracked wires based on the sample that we have taken and inspected under the microscope to identify the presence or lack thereof of pre-existing cracks. We use Monte Carlo simulation to develop the stress strain curves for the entire number of wires in the bridge cable, and the probability distributions we talked about a minute ago, and all that to develop a failure mechanism of the entire cable, in which the load carrying capacity of the cable reaches 0 at maximum elongation, and the maximum load calculated is the estimated cable strength. This is in a nutshell the process. Now, going towards the mother of all tasks, which is the forecast of life. We talk about crack growth under the fatigue loads, and in terms of that, we see this crack. I can tell you that the day we took this bridge wire out of the bridge cable, identified the number of years that this depth of crack survived the fatigue loads, And of course, we know the parameters. This is done with statistical work, and we have a subroutine to quantify the fatigue crack growth. What you see here is the Paris law. That calculates the incremental increase in the crack growth per n, which is the number of cycles. That is, of course, correlated with the life loads, and that is a function of delta K, which is in turn a function of the stress, the life load stress range, and the crack depth, and Y is the crack shape geometry factor that I talked about a couple of slides ago. And we are able to determine the life of that wire to a very high level of accuracy, and then the high level of confidence. Take that as a springboard to forecast the cable life. All right, so now you could appreciate how important the cracking is. It's very important. It is very significant. It has an impactful effect on the cable strength and on the forecast of cable life. Well, actually, I mentioned NCHRP 12-115. It basically says fractographic examination of wires is no longer required. So in other words, we will not know, or you as a bridge owner or as a bridge engineer tasked with this, you'll not know where the cracks are, to what extent they grew, and so on. Well, that's not the way to go in our view. As if for this crack beam, I would say that just don't mind the crack here, or actually, almost the whole web is fractured, and the bottom flange as well. The top flange is on its way eventually. You can see here, just give me the bending capacity of this beam. Does that make sense? No, it doesn't. Or for that Interstate 40 bridge linking Arkansas and Tennessee, just give me the capacity of this bottom chord. Of course, this arrow is totally redundant, but you see here, we averted the disaster over there, thank goodness. Or this 7-inch long crack at the shear connection of a cope beam. Just give me the shear capacity over here, away from the crack. It doesn't work this way. Speaking of the NCHRP, just to spend a minute here talking about the visual stages of corrosion, is basically talking about 4 stages of corrosion. Stages 1 and 2 quantify the zinc coating oxidation, and stages 3 and 4 talk about or describe the amount of ferrous corrosion that comes along with the process. That's all visual. It is subjective, and you can see the reference. This is 534. And by the way, we don't use this stages of corrosion. It's just shown here for illustrative purposes. I bring here the wedge openings, and all this, as I mentioned before, everybody just sees the wires along these wedges. So anything on these 8 sectors, the curvilinear distance between 2 successive wedges is a sector. All these 8 wedges, which form 90% of the wires, are conjectured, where you see these colors of the stages of corrosion. Nobody sees them. They are just conjectured over here and there, all over. So you get the point. So what gives? Well, actually, this visual evaluation of stages of corrosion is juxtaposed here versus the measured mechanical properties. This is actually referenced in New York State DOT report C0711, where we have the mechanical properties are taken from the testing laboratory, and all these stages of corrosion defined by the folks that did the NCHRP. For that case study, we did the cable strength by the BTC method, and other folks did the NCHRP methodology, and we are just showing that, juxtaposing that to show the kind of discrepancy. One would expect stage 4 to be weaker than stage 3 and stage 2. It is flipped upside down. Well, this kind of discrepancy is not happening for just a couple of wires. It's for the entire set of samples. I shows here one panel, but in that report that I'm referencing down there, you can see the entire 8 panels where all of them have this kind of discrepancy to one degree or another. So moving along, we see that in just about all the cable investigations we have worked with, that there is no correlation between the visual measure of corrosion and the actual measured properties, neither in tensile strength or fatigue life. Actually, I reference here a paper by a group of researchers from Denki University in Tokyo Denki University in Japan, and they studied the correlation between corrosion and fatigue strength of high-strength galvanized steel wires used for suspension bridge cables. And here is a snippet of the summary of the conclusion. It says that in the specimen obtained from the corrosion levels set in this study, fatigue strength showed results that were equivalent to or higher than those for new wire or of new wires. The tensile strength also showed similar results. So there you go. So that this is a kind of discrepancy that you would see with the visual corrosion. All right, so moving along here, what are the lessons learned from the numerous bridges that we have worked with? It's evident that cable-supported bridges are strategic assets with significant value to the economy and society, enabling social and business connectivity. Therefore, the assessment of residual strength and service life is of paramount importance to everybody, all the stakeholders, bridge owners, and the public. Only conducting in-depth inspection, sampling, and testing of wire samples from different lengths of the cable would provide the needed information for strength evaluation and forecast of life of the cable. A successful strategy for the preservation of bridge cables is a whole discussion, but some of these traits of a good preservation strategy is to perform periodic inspection, sampling, testing, and strength evaluation, because this will allow the bridge owner to intervene at the proper time with corrective measures to slow down degradation and to stay ahead of degradation. That is really key. And with several successive cable investigations along the service life of the bridge, the forecast estimate is honed, and you can get to more accurate assessment of the forecast. And any suspension cable investigation, from our experience, must include removal of the cable bands to examine the cable wires under the cable bands. This is one of the areas that are vulnerable to degradation. Experience shows that the reliance only on the visual corrosion-based approach could lead, and has led in the past, to costly and unnecessary measures. The cables are obviously the most critical element of the cable-supported bridges, bridge. Therefore, it's logical to use a condition assessment method that provides confidence, that actually looks at the measurable metrics of degradation without conjectured observations that would introduce inaccuracies in the analysis. With our vast expertise and successful application of the BTC method on numerous bridges, the method presents a reliable alternative methodology, and it provides independent checking mechanism rather than just relying on the NCHRP visual corrosion-based approach alone. This will provide the bridge owner with greater assurances when dealing with decisions regarding the results of internal inspections and strength evaluation. The BTC method's unique forecast of life capability provides unparalleled feature that serves bridge owner and help bridge owner with the preservation and the prolonging of the service life. And one very important element I want to mention here in a few seconds with some of the new bridges I mentioned, we were locally in the room where we helped influence some of the project specifications, and we contend that this will take us a longer way in delaying the wire degradation and prolonging the cable life. That's a very important element of the whole process. So if you have a new bridge, we can definitely assist in terms of that aspect. In conclusions, the conclusions here, the BTC method has been applied to evaluate and forecast the service life of the bridges I mentioned at the onset, Bronx Whitestone, Williamsburg, Mid-Hudson, Pierre Laporte in Canada, Fort Road in Scotland, and others that we cannot talk about here today. On the Pierre Laporte, we did the main cable, we did the prioritization of the replacement and the condition assessment and the forecast of life for the entire set of suspended ropes. One very important element I'd like to leave you with is that cracking is the, or if not a major driver only, it is the major driver of cable strength degradation. And then the application of the principles of fracture mechanics is essential. And of course, by that definition, the fractographic examination is a crucial step to identify the pre-existing cracks. The BTC method, we can say today it is the only method that provides identification of cracks or pre-existing cracks via fractographic examination. It does fracture-based analysis based on fracture mechanics, and it forecasts the cable life, and it applies to parallel and helical wire strand cables, and it provides condition assessment for suspension, cable state, bridge cables, and pre-stressing steel strands or pre-stressing girders. And that includes, of course, the forecast of service life. Finally, the BTC method presents an overall risk management strategy to estimate cable strength at high level of confidence. Here is the final slide that has my contact info and our website. Please let me know if you have any questions. I thank you very much for listening. Thank you for the opportunity, Atarod. I turn it back over to you.
I'd like to thank Khaled very much. I really appreciate the information. It was a fantastic presentation. And now we're going to move into our question and answer session. I'd like to introduce Paul Lyles, who is the Georgia State Bridge Engineer, former Georgia State Bridge Engineer. He'll be moderating our question and answer. He will be assisted by Jamal El-Kaisi with FHWA. Jamal will take over partway into the question and answer. So Paul, I will turn it over to you.
All right, Kathy, thank you. Khalid, are you there?
I am here. Can you hear me?
Yeah, we just can't see you.
Oh, okay. Hold on a second.
Okay, that's fine.
You can. How about now?
Yeah, there you are. That's good.
Right.
We did get a number of questions that came in pre-webinar. We have a couple that have come in here, and I will cover the ones that have come in before this time. Let's start off. This is a pre-webinar question. It says, has this method been used to investigate potential corrosion within grouted stay cables?
Yes, we're looking now at grouted stay cables, and the short answer is yes. And what we can do is just the grouted stays. There are two elements to address here. There is the free length of the cable, where you can go and just try to remove the grouting. See here, there is a hammer here, removing the grouting. We have to do that very carefully. You know, you're almost in the way of the hammer when the gentleman is trying to do that, and you do part of it as well, and where you can discover some of the wires. And sometimes we find the broken wires, actually, when we do that. So that's just the free length of the cable. Actually, one thing that I must articulate here, this is just for schematic purposes. You see the anchorage. I mentioned the anchorage because, relatively speaking, you would find more problems towards the anchorage because of the bending fatigue component. There are ways of going there carefully, trying to reach this level of the wires, and you might find a lot of wax and grease and inside the anchorage in these locations. It depends on the particular stake cable construction, and you can make a lot of get a lot of information from that. Okay.
Okay. Here's a sort of a cost question. This came in beforehand. Federal funding is sometimes tied to service life. Can the BTC method be used during design and budgeting to project service life in the interest of securing matching federal funds?
Absolutely. This is actually this is a great point. This is what I mentioned here in the lessons learned, where that we contributed to the project specifications. There are certain elements, and one there's more than just one element that dictates the longevity of the bridge wire. Being there, we used our BTC method and our know-how on the bridge wire material to specify certain aspects to prolong the cable life. So that is definitely doable. It's been done, and we're happy to assist in that regard.
Okay. Could you comment on time and cost to use the BTC method?
Well, the cost is very much comparable to the other methods. There is a nominal cost in doing the fatigue test and the fractographic examination, because we do a big part of the fractographic examination with our fracture mechanics expertise. So the cost is very comparable, and the time as well. In fact, this is what we do. This is our line of work, and in terms of time, we turn things around in short order.
Okay. How does the BTC method accommodate helical strand suspension bridges, or really any helical strand bridges?
Yeah. Okay. I want to bring the case, which is public knowledge, is not revealing a secret. This is the Waldo Hancock Bridge cables before they were dismantled, and when the bridge was demolished. You see all these broken wires. All these broken wires are basically embrittled. If you zoom in on the specific wires, all these broken wires and just everywhere were embrittled. You see this? Embrittled. The full diameter of the wire. Full diameter. So we can take this, apply the testing, and there you go. We apply the BTC method. We can take all these fracture surfaces and do the fractographic examination, identify the cracks, and do the examination. That could be done for any other cable stake bridge.
Okay. Is the BTC method destructive or non-destructive testing?
Well, actually, if we go back to, actually, I want to mention one quick thing here also for the Waldo Hancock that we looked at from the records, is the presence of micro cracks were dominant, which emphasizes that embrittlement aspect. Let me go back to the slides on sampling to answer that question. This is the very reason not to be destructive that we identify this pool of wire samples. So any wire we sample, we put back in with this very good methodology of installing a brand new wire with that turnbuckle, and there you go. The sample is taken out. You put a new wire back in, serving or carrying the same surface load, and off you go. There is nothing destructive about that aspect for the cable itself. Of course, the samples that we've taken, we do the testing on it and we move on, but rest assured that all your samples taken from that yellow donut that defines the pool of wire samples are said and done. Back in effect, carrying load.
Okay. Here's another question that came in beforehand. Does galvanizing or the zinc coating have an adverse effect on the BTC method results?
Well, not at all. Maybe the question I like to understand it, that what is the effect of zinc coating on the wire itself, and that's probably the question is that we find the effect of zinc coating on the behavior of the wire. Case in point, the proof is in the pudding. When we see that the wire has this kind of ductility or this kind of ductility and crack growth, that is all in the test data. That is the blood work that will show everything: the effect of zinc coating, the effect of embrittlement, the effect of growing cracks.
Okay, here's some new questions that came in. The first one here is it possible that some of the cracks in the scan of the cable or the scan of the wire were created while taking the sample?
Oh, no. You can identify that immediately. I mean, these wires with this kind of beach marks that develop over years and years and years, and they have certain feature. If someone is talking about necking the wire, first of all, we don't do that. We're very careful in doing the sampling, and that does not typically happen. And if there is by error, there is such an occurrence that I've never seen, basically wouldn't be quantified as cracks. I mean, when we look at this, if the person looking at this, knowing what they are looking at, they would distinguish a crack from a necked wire by a tool or whatnot.
Okay. And then along the same line, does the wedge opening cause any damage long term to the cable? No,
not at all. These wires are very sturdy, and the kind of wedges we use, well, sometimes some people still use wooden wedges, but these are fiberglass. So you talk about the hardness of this versus the wire. It's not even close. No, they don't cause any damage.
Okay.
No.
Okay. Then here's a question on your probability curve that you had. It says, how do you create the probability distribution for number of broken wires when you only inspect 10% of the wires, and of these, only a very few of them are broken?
Well, actually, the probability distribution shown here is not the probability distribution for the broken wires. This is a probability distribution shown for the ultimate strength, for instance. The probability of broken wires is a probability as a proportion of broken wires that is taken based on the number of broken wires related to or as a proportion of the number of wires you observe during inspection. You see what I mean? Yeah.
Okay. Now, here's another question. What are the differences between wires used in old cable bridges and new cable bridges? You mentioned the difference in strength. Is there anything else?
Yes. Well, in a sense, we have the strength now. I can tell you for the new suspension bridge, the latest suspension bridges we worked on, the ultimate strength is 1960 megapascal, which is about a little over 280 KSI. That's the minimum accepted. Compare that with 220 or 225 KSI. So we are pushing the envelope. But there's a big concern there, or big. Let me take that back. I don't want to say the word concern. There is a caveat to what we say here, because nothing comes for free, Paul. We get that awesome strength at the expense of reduced ductility. You see what I mean? So we push the envelope on the strength, but that actually induces vulnerability for the ductility axis of the curve. So when we increase the carbon content, and when the elongation of the grains is pushed further, you are imparting the distance between the grains, which is again reducing ductility. And the other toll to pay is allowing the atomic hydrogen to penetrate, break the interatomic bond, and cause the embrittlement. So this is part of what we need to be careful with going further, because we are getting very ambitious in terms of span lengths. With the last suspension bridge, we are actually more than quadrupled the span length, almost quadrupled the span length of the Brooklyn Bridge, and so on. And we are looking for longer suspension cables. So the basic short answer is yes. The strength is becoming much higher than the typical suspension bridges of the past era.
Okay. Are there any differences between the recent AASHTO guide that they've recommended for inspection and what you're presenting today?
Recent AASHTO guides. What is the title of that?
It says,
Which
yeah.
one?
Are there any differences between the recent AASHTO guide for inspection of wires and what you're presenting?
Well, actually, there are major differences. If I understand the question correctly, that it has to do with the proposed guidelines for cable inspection. There is that proposed cable inspection is based on NCHRP 12-115 I mentioned earlier, which basically says that you don't need to do the fractographic examination, and it's based on the visual assessment of wire. So we have serious concerns about this.
Okay, no, I see the difference now. One more question here, and I'm going to turn it over to Jamal. Some people have used ambient vibration to measure existing forces in tendons. What do you think about this method of inspection?
Well, it has some merit when you have a single strand or a single wire, and you can get some good feedback. But on a suspension cable, for instance, where you have the wire surrounded by other wires, and the interaction and friction between the wires would change the boundary conditions, it might not be spot on. It's a good guesstimate of the tensile stress in the cable. But remember, damage is a local phenomenon. And when you have these particular cracks and the crack growth, and I doubt that the ambient vibration method would capture that, because there is a redistribution of the stress in the remaining wires. So it has to be taken with a grain of salt.
Okay. It's 10 after. I'm going to go ahead and turn it over to Jamal.
Thank you, Paul.
And I think there are a few more questions that have come in, and we'll see what we can get here.
Thank you, Paul. Khalid, this is a great presentation.
Thank you, Jamal.
There's a couple of questions that came in during the presentation, and you touched on some of them. But if you want to elaborate, one of it about the stake cables, and it says, can the method be applied to individual greased and sheeted stake cables?
Yes, it can, because as I mentioned earlier, It depends on the design of the stake cable, the configuration. Then you bring boot at the deck level. We can maneuver around that and uncover some of the details particularly at the anchorage, and see what the condition is. So yeah, definitely can be done. Yeah, so we're doing some of that. Yes. Yeah.
Great. Another question came in during the presentation about post-tension cables, grouted post-tension cables. They say, any thought on the application of this method?
Yeah, there are, these are strands of pre-stressed cutter, and you see the wire breaks here, all embrittled, and these were taken and analyzing under the microscope as well, quantifying the cracking and what give here, and the analysis with the BTC method renders excellent results and very, very informative data and information to the bridge owners.
Great. There's a question came in which is not bridge related. It says, can this method be used for checking the cables for ski gondola cables?
For what, sorry?
This is the gondola, like the cables for skiing, you know,
yes,
for skiing.
It's applicable. Yeah, it's applicable to any cable that's made of high strength steel material. It has different, of course, set of loading and loading applied loads, but at the end of the day, the assessment of degradation and the longevity and all this, certainly it could be applied to that.
Great. I have a question on my own. If we go to sampling, to sample the wires, how can you sample the one in the middle? Not at the top, but the one at the middle.
Right here?
Yeah, around the middle. How can you sample?
Or here, for instance?
Around the middle, yes.
Like here, Jamal, you're talking about the middle somewhere here?
Yes.
Yeah, we don't do that. We don't recommend doing that. Even if we are able to go there and cut the wire. But the problem is, when you go back and to try to use these pliers and rudimentary tools, we cannot put the wire back in, and that will make it destructive and will provide void. And we try to avoid that at all costs. The return on that is not worth it. Yeah.
So the sampling would not be applicable to every location on the cable, but the one at the top you're talking about.
Well, actually, and that is for every method. It's not only a stipulation of the BTC method. We don't recommend, even though there was a particular cable, without mentioning names, where samples were taken much deeper, and I'll leave that as is. But this was after the facts. We looked at a case of that magnitude, and the good news is, for most cables, not all of them, there's some exceptions, the tight compaction close to the center would render these wires stronger, so it's statistically safe to take wires on the outer ring where you can put the wires back in.
Great, thank you. That's all I have. Back to you, Kathy.
All right. Thank you, Jamal. Thank you, Khaled. If I can just have you stay with me, Khaled, for a minute. Quick camera.
Okay. Can you see me? Yeah.
Yes, we can. So certainly very good presentation.
Thank you.
Tough, important problem, and a tough problem really to handle, but nevertheless, I mean, that was very good explanation and shedding some light. So We thank you for the presentation.
Thank you for the invite, Dr. Rose. It's a pleasure.
We hope that, again, the deadline to submit a one-line abstract for the 2024 World Bridge Engineering Conference is May 30. So we hope that you consider submit an abstract if you have not. The copy of all the presentation, including the news and what will be included in the World Conference as far as the keynote, the speaker, and so on, will be posted on our website. So again, thank you, and we hope to have you back with us for our next monthly webinar that will be on June 13 on the press brake bridge system. So on that note, we will conclude this webinar. Again, thanks to everyone that participated. Thank you.
Thank you.